Yeah, fine. Okay. So once you have downloaded this, then we have got different options of our automata theory and formal language. For CO1 and CO2, we require this finite automaton, Melly machine, More machine, then grammar, then regular expression, and regular pumping lemma. These are the CO1 and CO2 covered here. Regular, let me repeat, finite automaton, Melly machine, More machine, then grammar, then regular expression, and pumping lemma. Regular pumping lemma. These are the different options in our CO1 and CO2 that we will cover up, try to cover up in this particular class. And if it doesn't cover up, then we will take another session if required, maybe offline. Okay, maybe on Saturday we can take it. That is up to if it is possible. Okay, so let us start with a finite automata. Let me open up a word so that I can write something. Okay, let me click on this finite automata. So when you click on finite automata, you will get a window like this. So it has got the different buttons. This is your select button, attribute editor. You can change the attribute of the different components. This is your state creator. This is your transition creator. If you want to delete anything, this is your undo and this is your undo. Click anywhere to undo the things. Is that clear? I hope it is clear. This is just the things. Let me take one particular simple problem and let me create the solution to that. But before that, what these things can do, I just explain. If I Because these are event oriented, so that is why you have to click on this button, and if you place it, you can place some states here. Okay, like this. You can place states, any number of states anywhere. As long as it is clicked, you will go on creating the states. Suppose I want to create a transition between Q0 and Q1. I click on this transition editor and click on this Q0. Clicking on, just drag it to Q1. So it will ask me with what string it will go from Q0 to Q1. I'll say 0. So it will show me. Again, I'm doing it from Q1 to Q4. Again, I will drag. It will show. It will ask me with what value it will go from Q1 to Q4. I'll say it's 1. So it's 1 it goes here. Right? Suppose I want to delete the rest of the states. Just double click on it. It will be deleted. Double click. Okay. And then here, in this particular case, I want to change the attribute of Q0 as a initial state and Q4 as a final state. So then I will click on this attribute editor and I will right click over here and click on initial. So this becomes initial state. I will right click here and click on final. So this becomes a final state. Okay. So ultimately what happens in this way, my automation or the machine is being created. Okay. Now, in this case, I want to find out what is the string accepted by this particular machine. Even I want to create some loops. Like, for example, if I want to create some zeros here, the zero loop is to be created here. Just click on this. Without dragging, click on this and put a zero. So, a zero is being created. Okay. Suppose if you have 0 and 1 both on this Q4, then I'll click on this Q4 first. So this will give me a 0. This 0 loop is given. I need one loop also. Again, I have to click here, and again I have to click. So this becomes now 0 1 loop, right? And now I want a suppose this is a DFA I am trying to create. So I want to find out whether for the sigma 0 and 1, this Q0 to Q1, all the 0 and 1 transitions are there or not. If you see from Q0 to Q1, there is a 0 transition, but there is no 1 transition. So I want to create a 1 transition. So I will put a new state, and then from Q0, I will go here with a 1. Which is basically Q2 is a trap state. Okay. And here in this particular case, what happens? This machine should accept all strings starting with 0. If it doesn't start with 0, then it will not accept it. So what it can accept? 0, 1, it can accept. 0, 0, 1, it can accept. 0, 0, 1, 0, 0, anything that starts with 0, it will accept. Now this is what I think of. But how do I verify this? To verify this, that what strings it is accepting, I click on input and multiple run. If I have got multiple strings, then I will share. Okay. Here the input and the result is being given. That means if I give the input here, whether it will accept or reject, because the output of this machine is two strings, either accept or reject. So, as I have mentioned, this automaton is meant for accepting all the strings starting with 0. So, suppose I want to check whether 10 is accepted or not. Press enter, you will come to the next one. Again, you type out 01. Okay, let me test these two. Okay, so if I test these two, then what happens? What I'll do, I'll just click on run inputs here. When I click on run inputs, it says 10 is reject and 01 is accept. So that means my machine is working correctly now. Okay, so this verification is also possible with this particular software, right? We have created a DFA. We have verified this DFA with the input strings to check whether this is accepting or rejecting. And since these two strings are the basic strings that can be properly verified with the rejection and acceptance, that is why I assume this particular machine to be correct. Okay, so this is what all about your TFS. We can have many different problems related to TFS, and then we can discuss some more problems related to this. So for example, okay, suppose I want to create a string DFA. Look at this particular string. L equal to W. W means a string. It's a string where the string contains 0, 1 inside it. Okay. So 01 can be present anywhere. It could be in the beginning, it could be in the middle, or it could be at the end. But if 01 is found, then we will be able to do that. Okay, let me see if I can do this. W contains 01 in it. Now what is this DFF? This DFF is all about all the strings that starts with 0. Okay. So what I'll do, I'll make small changes into this particular DFA and I'll see that it is working properly. Okay. So what I'll do, I will remove this particular dead state. I will trust it. Okay. See the changes. Look at this particular DFA. This DFA accepts all strings that starts with 0. Whereas our problem statement says that we have to design a DFA that accepts all strings where 01 is within it. So I will just remove this, and what I'll do, I will make small changes like with 1 also it can start. The string can start with 1, but if 01 is present in the middle, I don't have any problem. Okay. Now, what about suppose 1 0 0 1? So 1 0 0 1. See the strings. What are the strings here? The strings will be 1, 0, 0, 1. If you see here, 0, 1 is present here, so this is accepted, right? Then 0, 1, 0, 0. Okay. What else can be there? 1, 0, 1, 0, 0, 1. So 0, 1 is present here. Even 0, 1 is present here. So anywhere it is present. So all these strings will be accepted, right? Because 0, 1 is present in the beginning, in the end, in the middle. Anywhere it should be present. Okay. So let us try this. So in this particular case, 1, 0, 0, 1 is accepted. 1, 0, 0, 1 is accepted. So this is accepted. I am thinking this. I'll test later on. Okay. 0, 1, 0, 0. So 0, 1, 0, 0. Accept. So this is again accept. Okay. Then 1, 0, 1, 0, 0, 1. 1, 0, 1, 0, 0, 1. Accept. So again it is accept. This is what I think of. Okay. Good. Let me try out. So I will go to multiple run. Okay. Delete these things. Press delete. Click on here and press delete or click on clear. The same thing. Then I try out the strings 1, 0, 0, 1. 1, 0, 0, 1. The second one is 0, 1, 0, 0. 0, 1, 0, 0. The third one is 1, 0, 1, 0, 0, 1. 1, 0, 1, 0, 0, 1. Okay. Let me run the inputs. They are all accepted. Okay. So with a small change into this particular DFA, now the DFA accepts different set of strings. So hence, it depends on my language capability, what kind of string I want to get accepted by my machine. That is what I need to do here. So this is all about your DFA. I think you understood it. Okay. Now, the DFA has got very minimum processing capability in each of its states. The states doesn't have enough memory. These states doesn't have enough memory where they can count the numbers. So DFA has got this particular serious limitation. That means it cannot accept any strings that has equal number of zeros and equal number of ones. So uh, from this point of view, let me design another string, another language, L equal to, is another one, L equal to W such that W has an even number of ones. W such that W has an even number of ones. Now, you see, this particular language creation requires counting. I have to ensure that all the number of ones present in my string has to be even. So let me take some strings. So 1, 0, 0, 1, it should be accepted. 1, 1, 0, 1, this should be rejected. Why rejected? Because here two ones are there. Two ones. Here three ones. So this 2 has to be even, this 3 has to be even. But here it is odd, so that is it should be rejected and this should be accepted. Right? I hope you understood the problem. W has an even number of ones. So that means our machine, what it will do, it will count the number of ones and then it will accept it only when the count is a even number. Okay. So since I'm counting and the count has to be an even number, I will use a simple mathematics to find out what is an even number. Can you tell me what is an even number, all of you? Anyone? Except Arvind. What is an even number? Hello? Is there anybody?
Yes, sir.
Yeah. Tell me. Kavyasri, tell me what is an even number?
Sir, once again the question, please.
The question is what is an even number?
Even number.
Yeah.
Anything that is divisible by 2 is an even number.
Okay. How do you know it is divisible by 2?
The remainder should be 0, sir.
Correct. So the remainder should be 0. How do you know it is not divisible by 2? Hello. Kavyasri, how do you
If
know?
remainder is not equals to 0,
Not equals to 0 means it is infinite, you are saying. It could be 1, 2, 3, 5, 7, 9, anything. Is it so, Aditya? If I divide a number by 2 and it is not equal to 0, it could be anything. Can you be specific?
Rather than two multiples, if the number is not equal to two multiples, then it is not divisible by 2, sir.
Oh, I understand. Is what you told Sitanya, na? Sitanaya. What is your
Tanaya.
name?
Yes, sir,
Sitanaya.
Tanaya.
Yeah,
Yes, sir.
Sitanaya. Actually, you are correct. Whatever all of you are telling are correct. But actually,
Yes,
I
sir.
want to know one part is clear. If you divide a number by 2 and the remainder is 0, then it is divisible by 2.
Divisible by 2 and it is an even number.
Even number. Correct. I am going to the negative side. That means if it is not divisible by 2, what is the remainder?
non-zero
One is
element.
Yes?
one is the remainder.
If it is non-zero,
Lakshmi, exactly, it is the remainder is 1. So if you divide a number by 2, the remainder could be either 0 or 1. It cannot be anything else. You take any number, divide it by 2. If it is divisible by 2, the remainder will be 0. If it is not divisible by 2, the remainder will always be 1. That is what the property we are going to take to design this particular machine. So we have got two states now. One state that represents the zeros and the another state that represents the ones. That is what my machine design will start. Okay. So the machine design is something like this. I don't require the third state, so I'll just remove this. Okay. And I'll start with, I also need these things to be removed. I'll start at press, start, so two states I will take. Okay. One state representing the remainder 0, another state representing the remainder 1. So now tell me if remainder is 0, it should accept or reject. Hello. If the remainder is 0, if you take a number and divide it by 2 and the remainder is 0, it should accept or reject.
It should accept, sir.
Correct. It should accept. So that means all remainder 0 numbers, that means I take a number, divide it by 2, then this is the state that represents my remainder 0 state. So what I'll do, I will just uh, create a transition. If the remainder is 0, then it will be here. Okay. So you see a binary number starting with all zeros, all 0, 0, 0, 0. Even 0 is also an even number because if you divide 0 by 2, the remainder is 0. So it is 0. Now suppose if I get 1, what I'll do? I'll go here, right? Now, given this particular, all of you can see this? Yes?
Yes, sir.
Yes, sir.
Yeah. Now, if you look at here, in this particular case, Q0 is 0 state. That means it contains all the strings whose remainder is 0. And this is the state that uh, contains all the strings whose remainder is 1. Now tell me which one should be the accepting state, Q0 or Q1?
Q0.
Q0. So I go to accepting state. So from where I will start?
Q0
From
itself.
Q0 itself. So it will be an initial state. So Q0 will be my initial state, Q0 will also be my final state. Okay. So now in this particular case, I have designed this machine where all zeros will be here and all ones will be going to Q1. Now suppose if I take a binary string 0, 1, what does this mean?
Q1 is the output if you
Q1
take
is,
0, 1.
yes. Okay. So now what happens in this particular case, suppose if I take 0, 1, if I take the binary string, let me take a binary string 0, 1. What is the decimal equivalent? 0, 1. What is the decimal equivalent?
1.
1. Right? Very good. What is the decimal equivalent of 1, 1?
3.
What is the decimal equivalent of 1, 0? 2. Now, out of these three numbers, decimal equivalent is your 1, 2, 3. Which should be accepted? Which string should be
3
accepted?
should be
If I give
accepted.
zip,
3, sir. 1, 1.
why 1, 1 has to be accepted? Are we counting? How many ones are there? We are taking a binary string whose decimal equivalent has to be divisible by 2. Look at the problem.
You said even number of runs, sir.
Okay? Even number of ones. Okay? Is that clear? So, this 1, 1 has to be accepted or not?
Accepted.
Anyone? Why it has to be accepted?
Because there are 2 ones, which is an even number.
Correct. So we are counting. We are counting the even numbers. Okay. So that means let me come to this particular window again. In this particular case, if there is a single one, I am here. So it is because single one is a count of one and it is odd. With double one, I come to here. Right? And in between, if any zeros are there, I stay here. Okay. Will this machine count the number of ones and it will accept only when the number of zeros, the count of number of, the count of number of ones is an even number. Is it doing so? Please check it at your side. Now let us test it. Input, multiple run. Let me take all these strings. The first string having two zeros, two ones. The second string having one one. The third string has got three ones, and let me take 110 110 the bigger string. How many ones are there? 2, 3, 5, 6, 7, 8. This should be accepted. Let me run. The output is good. I hope it is clear.
Yes, sir.
Others? Any doubt till now?
No, sir, is clear.
Okay, very good. Let us take another simple problem. Design a language L equal to W such that W is divisible by 3. For sigma equal to 0, 1. So the first thing is that W is a binary string. The first information is W is a binary string. So when you convert W into decimal, that should be divisible by 3. So again, we have come to the same type of problem, but a bit different. So let me take the binary string, and after converting into decimal, then divisible by 2 remainder. Okay. Binary string 0, 0, 0, 0. Any combination of 0. What is the decimal? 0. What is the remainder when you divide by 3? 0. 0, 1. What is the decimal equivalent? 1. What is the remainder? When you divide by 3? 1. Then 1, 0, decimal equivalent 2. What is the remainder? 2. Okay. Then 1, 1, decimal equivalent 3. And what is the remainder? The remainder is 0. Then 1, 0, 0. What is the decimal equivalent? 4. And what is the remainder? 1. Like this. It continues up to like this. So now, if you look into this particular design problem, you will see that we need to design a language where it accepts the strings W, which is divisible by 3, and W is a binary string. So since this is the case, so we will have to take into this discussion into implementation. That means a binary string, which is a combination of zeros, should uh, be accepted, because when you divide 0 by 3, the remainder is 0. Okay. So that is why what we will do, we will first look into the remainder. If you look into the remainder, whatever may be the number, the remainder is always either 0 or 1 or 2. Right? So three different possibilities of remainders are there. If you divide any number by 3, any bigger number by 3, you will get 3 of the remainders. Either it could be 0, or it could be 1, or it could be 2. Okay, so we will design a machine with 3 states. One state representing remainder 0, another state representing remainder 1, another state representing remainder 2. Okay, let me go to here. So we need 3 states now. So I will delete all these things. I will do the place again. Okay. I will do this, primary and initial, and make 3 states. Here, fine. So now what we'll do, all the remainders 0 stay here. If it's a remainder 0, it comes here. Okay. If it is a 1, that means I am now talking about what? I am talking about these binary strings. Okay, if it is all 0, remains in Q0. If it is 0, 1, If it is 0, 1, then what happens? You go to here. Why? Because for 0, 1, for 0, 1, the remainder is 1, and we have this as the remainder 1 state. Right? For 1, 0, for 1, 0, when the remainder is 1, 0, sorry, when the string is 1, 0, the remainder is 2. So it should go to this state. So 1, then, okay. Next, we'll go to the next one. If it is 1, 1, it is 3, and its remainder is 0. So from 1, 1, and 1, it should come to here. Right? So up to this, I have discussed 1, 1, up to 1, 1. The next one is 1, 0, 0. So when it is 1, 0, 0, and it is 4, and the remainder is 1, so it should come to here. So 1, 0, 0. So that means from 1, 0, 0, I should come here. In this particular case, what happens? Look at the remainders. For 0, remainder is 0. 0, remainder is 0. For 0, 1, remainder is 1. 0, 1, remainder is 1. For 1, 0, remainder is 2. For 1, 0, remainder is 2. For 1, 1, remainder is 0. For 1, 1, remainder is 0. For 1, 0, 0, remainder is 1. 1, 0, 0, remainder is 1. It is working perfectly. Our design is as per our discussion. Next part is we need to find out which one will be the initial state and which one will be the final state. Okay. Of course, we'll start from Q1. And since all the remainders who's having 0 will be accepted, so this will be your accepted state. This is what we are thinking. Let us try it. Good. Multiple one. Let me clear this and let me try out with first our all strings 0, 0, 1, 1, 0, 1, 1, 1, 0, 0. Let me try out with these four strings. 5, 0, like that. These are the four strings I am trying first and running inputs. Is it working? Let's check it out for yourself.
Sir, you didn't mention if what will be the output if the Q2 state is 1. You have to self-loop for the Q2.
Ah. Okay, fine. We'll go to that. But first of all, let me talk whether my thinking is correct or not. Our thinking, whatever we are thinking from the remainder point of view, is correct or not.
Okay, sir.
Okay? So let us see. 0. All zeros accepting. 0, 1 rejecting because we are reaching 0, 1. We are rejecting here. 1, 0, 1, 0 rejecting. 1, 1 accepting. 1, 0, 0 rejecting. Okay? So this is what happens. But in this particular case, what happens? It may happen that after this, after reaching to Q2, see if you look into this, it is not a DFA. It is not a DFA. Why? Because for this state there is a transition for 0 and 1. For this state there is a transition for 0 and 1. But for this state there is only a transition of 0. There is no transition of 1. So I have to make a transition of 1. If 1 is here, I will take it. Now let me check it out with multiple strings. Let me take multiples of 3, 15. 1, 1, 1, 1. This is will be by 1, 0, 0, sorry. 1, 0, 0, 1. This 1, 0, 0, 1. 9. It is also divisible by 3. Then 0, 1, 0. This is 10, not divisible. 1, 0, 0. This is 8, not divisible. And Let me try one with this. Okay. Do you see it is working? That means we are able to design DFS using this particular. Okay, very good. Okay, now I think Visul, are you there? Aditya, Bhavana.
Yes, sir.
Okay. So have you understood how it has been done?
Yes, sir. Yes, sir.
Yeah. Pramod Lakshmi, are you there?
Yes, sir.
Understood how it has been done?
Yes, sir.
Very good. So this basically uh, about your design of DFS for your uh, language, whatever language is being given, you can be using. Okay, let us now proceed to design of a matrix. So I'll close this. I will stop it. So I'll return to this. Okay. So when I return, NFA can also be done using the kinetic. So I'll again click on kinetic. Okay. So let me design NFA. This part is over. We'll start NFA. For language, design an NFA for the language L equal to W, such that third last symbol of W is a 1. Third last symbol of W is a 1. So what does this mean? This means starting from right, the third position must be a 1. So that means if I have got uh, 2, 3, 4, and the 4 positions, then this needs to be a 1. 1, 2, 3. Starting from right, this has to be a 1. Before this, okay, out of this could be 0 or 1. This has to be 1. This has to be 0 or 1. And this has to be 0. This is what the case is. Look at here. This is fixed. But the rest of the things are either could be 0 or 1. Okay. So we will design this. There are 4 states I require minimum. So what I'll do, I'll place 4 states. 1, 2, 3, 4. Okay. Then what happens? Which has to be a 1 in this particular case, where I have to put a 1. This is my fourth location. And this is my 1, 2, 3. Right? From right, this is my 1, 2, 3. So here I will put a 1. So I will put a 1. Look at here. This 1 is fixed. 1 is fixed here. Okay. Now, before that, any 0 or 1 could be there. So this will be a loop with 0, again a loop with 1. Okay. After this 0 and 1, so from here I'll go with a 0, again I'll go with a 1. From here with a 0, and from here again with a 1. Okay. So if this is fixed 1 and this is 0 1, this is 0 1, you put that as a 0 1, then this will be accepted. So this will be my accepting state and this will be my convention. Okay. Now this is a NFA. Can you tell me why? Can anyone tell me why it is an NFA?
Sir, what's the question, sir?
Why this is an NFA? Why this is an NFA?
For Q3, there is no 0 1.
Okay, this is one part. Another one. This part is verified. Okay. Anyone else who could tell me why this is an NFA? One part identified, Q3 doesn't have any transitions for 0 and 1, that is why it is an NFA. This is partly true. Another part is also there. Can you tell me which one is that? Yes. Gita is there. Gita, Harsavarga, Suman, Lohit, Yajneshwar, Pavan, Ruchita, Snabhyasri, Rupasri. Are you there? All these are present here or just logged in and went to?
We are there, sir.
You are there. Okay, tell me which one is your, in this particular case, which one is your non-deterministic? If you look into here, you'll see that this part is identified by Arvind. Okay? So here, in this particular case, you will see that there are two parts for one. When you have a one, you have a transition from Q naught to Q naught, and for one, there is a transition from Q naught to Q1. So multiple transitions are present here also. So this is your non-determinism. This is definitely non-determinism, but this is also a non-determinism. When in NFA, you need not to provide all transitions. Okay, so that automatically means it's a rejection. But in this particular case, there is a multiple transitions. For one, there is a transition from Q naught to Q naught. Also, with one, it goes from Q naught to Q1. So that is why it is also a non-determinism. Okay, but Q naught cannot be an accepting state. So just remove this. This will be your initial state. Okay, let us see whether all these strings are accepted or not. If I take only one string with one not in the third symbol, a multiple one, so this would be accepted, this would not be accepted, this would not be accepted, this would not be accepted, and 0, 1, 1, 0, 1. This would be accepted, then 1, 0, 1, 0, 0. This would be accepted, okay, and then the input, and you see the output. Third last symbol is A1. Okay. So this is how you design your NFS. Okay. So I have designed an NFA. Now I want to convert this into DFA. I can convert this NFA to DFA. So convert to DFA, right? I'm doing it again. This is your NFA you have designed. Convert to DFA. Okay. And this is your expand group on terminal. This is your state expander. So click on here and click here. It will expand the state. It will expand another state. It will go on expanding all the states. I think I have done everything. So let me rearrange this. Okay. Did you see this? This is your NFA. This is your NFA and this is the equivalent here. Done. The DFA is fully built. It will now be placed in a new NFA. So this is placed here and I will paste it. The same thing that we got in NFA we also got it in DFA. That means this is equivalent to the given NFA. So the NFA and this newly built DFA both are equivalent because they accept the same language. I hope it is clear. This is how you want to convert an NFA to DFA. So I think it is clear. This one is over. So what we'll do, we'll now go to NFA DFA is over, conversion is over. Okay. We'll now go to regular expression. So click on regular expressions. Okay. So here you can have regular expressions and from there you can have the NFS and from there you can have the DFA. So suppose the regular expression is A plus B whole star. Writing this A plus B whole star. Okay. A plus B whole star. Suppose this regular expression is given, first I will convert this into NFA, epsilon NFA. Convert to NFA using Thompson's techniques. So convert to NFA. This is your the conversion process. Look at here closely. First what you did, two states are created. From Q0 with A plus B whole star it goes to Q1. Okay. Then I will click on do step. So what happens here? In this case, it goes like this. See. In this case, what happens? From Q0, if epsilon transition goes to Q2, from Q2, if A plus B goes to Q3, and from Q3, if epsilon transition goes to Q1. Then, from Q0, if epsilon transition goes to Q1, and from Q1, if epsilon transition goes to Q0. Okay? Then again, this step. Then, it is A plus B expanded. according to your functions construction techniques. If you are studied, you will get A plus B is that. Okay. So this is your okay. This is your complete epsilon n A plus B whole square. Now we click on export. This will be exported as a epsilon n of a convert to DFA. So when I click on complete, it creates a DFA. Okay. So these are all different states. 0, 2, 1, 4, 6, 5, 3, 1, 0, 2, 4, 6, 2, 0, 7, 1, 3, 6, 4. All these are different states. 0, 2, 6, 4, 5, 7, 3, 1. All these are different states. So this is the complete DFA where this DFA is equivalent to your N. Okay. This is A plus B whole square. This is how you can convert your NFA to DFA. So first what we did, we tried a regular expression. This regular expression is converted to epsilon NFA, then that epsilon NFA is converted to DFA. Okay. So then let me do, okay. So this is my DFA, right? I will convert this into regular expression. So convert to FA to RE, become FA to RE. Okay. So make a single non-deterministic final state. So how many final states are there? 3 final states are there. Okay. So what I will do, I will create a another state. Let's create state. So this becomes the final state. The rest of the states are non-final. Then what do we do? Put epsilon functions from old final state to the new. So I will put the epsilon functions from the old final state to the new. So this is our okay. Then the old functions state to okay. Then wherever any transition is missing, put a lambda transition or excess transition. So here we can missing 5 transition, here we can missing 5 transition, and anything else is missing from here to here is missing 5 transition, and here to here is missing 5 transition, and here to here is missing 5 transition. Then what else is missing here, and here to here is missing another 5 transition. So all cancels out. Then I can make it very specific. Okay. So generalized functions are finished. So it will be change type or variation. So this is how your conventions will are used. If you are given the DFA, you can convert into regular expression. Here we are not using Latin's theorem. This is basically uses the standard notion. Okay. So this is your regular expression. All these things we have completed. Next, what we will do. I think we have completed this. The rest we will do it in the next session. Okay. I think we will wind up early.
Okay, sir.
Thank you all. Is it recorded? Please give me the recording.
Okay, sir. I'll give send you, sir.
Yeah.
That's